Thank you, Sim, for the kind introduction. Thank you, Sile, for the invitation. Do I have a clicker or here is this one?
It's this one. Sorry.
Nice. No, it's the first time I dare traveling without my laptop and fully relying on a Google slide presentation. And before we had a problem with the videos that we could fix quickly. I was a bit nervous. Okay, let's see if it works. No. One more. Okay, good. Let me start with this slide. This is an artist image, stage image by a friend of us, Jules Spinach. It's showing an industrial robot, so a common machine you use to produce cars, mainly, but also many other things. With a human, and the human is not just a random human, is our first employee at ETH almost 20 years ago. And they are, so the image is staged in a way that you should never show to an industry person, because this is a thing you shouldn't do. You know, this machine on the picture is extremely blind, extremely fast, extremely big and strong and unpredictable. So this is a deadly setup. But we like the image, and we're using it over and over again because it shows a thing that is fundamental to our thinking, and it's the relationship between humans and machines. So this deeply intertwined story between two ends of producing almost everything. So you need tools if you wanted to produce something. Doesn't matter how complex or how technological what you are trying to achieve is. But at the same time, this story is also extremely problematic, because often we relate to the machine or to machines in general and robots specifically in a competitive way. So we see our position in the world, our revenue, our existence endangered by this other species. While this shouldn't be like this. It hasn't been like this since ever. It's a thing that came up with Industrial Revolution. Industrial Revolution is this singular moment in history where many things happen. We have more energy, we have more material, we have abundance of things. And this is thanks to machine, but at the same time the machine take something away from us, the understanding for how goods are produced. And this, of course, is a slow evolution, happens over 250 years. Henry Ford isn't there day one, but at a certain point introduces the assembly line. And this has gone on like this until very recently. And although in post-industrial times in which we live, this equation has to be reformulated, we still instinctively react in this way. If I show this picture, maybe not this picture, it's an artist's picture, but if I show a robot producing something, a lot of people react with the fundamental question, okay, what about us humans? Okay, but this machine is actually what we bought 20 years ago when we tried or started to research and experiment at ETH in constructive systems. And now we come to the title of this lecture that fits very well what we have been done. So I didn't have to think a lot or to change things. We wanted to find out how the introduction of a machine like this robot would change the relationship not only to the things we produce, but also to the way we think about design. Good. Now, I have to make a very short excursus that is a bit didactic. After it will be just project, just to explain how we understand, or maybe understood. Now things are starting to change slowly, but 20 years ago this was clear, the relation between human and machine in a positive way. So you have architecture. This is a brick wall. The brick is a material that we never considered until we brought the robot as an architectural material. Then it became very dear to us. But it's interesting, it's a beautiful thing because it's probably one of the oldest, very systematic construction systems. And the question is, if you design with it, how are you going to describe it? It's the question of notation. And there are many different notation. You can write, you can draw, you can program. And this, what you see here, probably is the most direct one. If I would ask a kid to draw this one, it would produce the thing on the right, and everybody understands that it's a brick wall, but it's a notation that is very unpractical in construction, both in designing, but then specifically when you want to have somebody else, the mason or a company, to build this for you. Because this description here on the left is way too complex. Takes too long to produce, and it's very unpractical when you build, because you cannot measure each single brick in here. While there is a very strong and direct logic inscribed in this drawing that we can communicate with the concept of the bond. The bond is an idea that has been developed throughout history, construction technology history, that describes nothing else than a set of rules. So how it describes directly how something is done. And this allows us to think about it, to draw it theoretically. I mean, this is a consequence of this. It's not just a random pattern, it's a construction pattern, and it's extremely robust. So it's small, it's reduced, it's compressed, but it's robust because basically there is nothing I can do wrong. And it allows me to describe architecture with the addition of very few parameters, like the height and the length of the wall, plus the type of brick I want you to use, fixes everything. Now, if we want a machine and not a human to build a brick wall with the same simplicity and directness, we need to describe it differently, because bond is, it's part of a language, human language. It's a thing that machine, for sure doesn't understand. A robot for sure doesn't understand, but also ChatGPT doesn't understand what a bond is. Can extrapolate, but cannot really understand it the way we do. But there is a notation, and this is nice with this brick stuff. A notation that is identical and belongs to the realm of machines in the same way as the term bond belongs to the realm of humans, which is just two nested loop, describing again the same way the mason would perform it, what to do. So put the brick at a certain position, then put the next brick next to the last one, go on until you have reached the end of the space or an obstacle or the length. I want you to do this. And then you jump back. This is the second loop or the external loop. You move up by the height of a brick and you shift by half a brick. And this does this. Now, this is a nice symmetry, identity, but it doesn't help, because we were interested in finding out what the difference would be. So when does the system change? The system changes if we add something to this small algorithm, which is banal. It's it's 2 lines, could be less. We do some calculations, and now 2 things happen. First, there is design coming into this algorithm. Before it's not. Before it's just a convention, it's just a system. Now this person, and this only a human can do, thinks of what could I change to this constructive system? How could I manipulate it? And he decides for a rotation of these bricks. Adds these 2 small lines. Everything else is identical. It's just the pink stuff down there that now gets added. And now the equation changes fundamentally, because what before was ideal for being built by a human, just the same rule repeated over and over again with the same visual reference. We are strong in putting one thing next to the other. We can be very quick, very efficient. Now, outputs for each single brick, not just the position in space, but also its rotation. And this rotation is absolutely not intuitive, because it's following an algorithm or a calculation, whatever, that is completely arbitrary. There is no way to recognize it, or to extrapolate it from the position of the last one. And now you could say this is a very small change, but it's gigantic, because the thing that before was conceived to be built by human now has been taken out of the domain of the human and put into the domain of the machine. At the very core of the domain of the machine, because you don't need any artificial intelligence here. It's just a controller that controls 6 motors that are axes. Of course, it's very high tech, to have this robustly perform over years and years. But at the end, it's banal. But this machine has the ability to put an element in space and doesn't distinguish between simple and complex positions. So this also the very notion of complexity is renegotiated here. Okay, and this allows us at the end of the day, now I come to an end, to directly connect the creative act of designing, that is our human capacity, to the capacity of machines to perform complex actions in space without caring about the degree of complexity. And this direct connection, shows us 2 things: that suddenly this competition between the human and the machine, so that here the human is not substituting the machine is not substituting the human. They're operating on their own domain where they are strong. Now you could say this is romantic, is a bit naive. You might be right to a certain extent, but it's still worth thinking what it means, because we are doomed to interact with machines, and the longer we interact with machine, the less we are aware of it. And to understand when, in which situation we do more. So when does 1 + 1 give 3 and not 1.5? This is very important, because it's not always obvious. Here you see the result. This is when we probably first come up with the notion of digital materiality. That back then was a strange combination of 2 words that didn't fit together. We did it on purpose. Now, 20 years later, I sometimes read about digital materiality. I think it would be normal, a concept, an established concept. But today will not talk about digital materiality, but this is more, what does it do to architecture? Here, 2 logics come together that normally don't belong together, but they push each other. They do something that goes beyond, computer graphics, 2-dimensional representation. This is material in space, made visible by light, depending on the position of the light source and the observer. So we are at the very core of what architecture is. Good. So this first thing example allowed me to establish how we relate and think about machines, and also that this relation is part of a system. If we think of constructive systems, we stop thinking of just construction, just how do parts meet in space, how do we screw things together. Constructive systems are something much, much bigger that goes into question of energy, question of labor, question of time, societal question, who does what, when, where do parts come from. And of course, machine and our ability to interact with this machine, to talk to this machine, and to decide who does what. Here in this example, this was a winery we did with Andrea De Platz as a friend, just a few months after the first experiments, where we decided to have the machine deposit the bricks and putting the glue. And often are asked, why didn't you automate the guy, you know, putting the brick on the thing? And if they, because we're not engineers, you know, it might be possible, but it's, you know, not very interesting, and it wouldn't change anything to the end product. Yeah. Maybe I move forward here. Yeah, there you see the result. This was the first. This is, you know, these parts are not structural, they're nothing. They're just screens that allow air and light to permeate. It's a winery, so it's what basically these facades should do. But they have this pattern. I cannot now explain how it was generated and what the design thinking behind hypothesis behind it is, but I just wanted to show you how complex things become with such a simple manipulation. You know, you move a bit or you wait half an hour, the light condition changes, you go closer, you go inside, and you know, you're sitting and then they disappear. You couldn't say that there is one facade, there is an infinite amount of facades here that are inscribed into this very, very simple and banal and fundamental stacking of bricks. Yeah. Next project, this is a project I rarely show, but here it fitted the constructive systems because it allows to extend the concept of system to the design system and to this relationship between a constructive system and design system. Here we go, we take the robot. It's not ours, actually, it's we landed it from a company, and we bring it to the Biennale in 2008, to the Swiss pavilion. And we had this machine building brick walls in front of the pavilion for a while, and then we were assembling them inside in order to create a structure and exhibition. So basically it's exhibition design what you're doing here. And here what I want to talk about is the design approach. So we had this ability to program bricks so that the robot could then directly, and it programmed them in a complex way, not just a stretcher bond, a few square meters, but you know, this brick following a curve and being rotated and so on. And here we decided, when we were asked to do this architecture, this exhibition design, we decided not to design the form, the final form, but to design a system. Because we were aware that these things need to change, to be flexible until very late, because exhibition design is like this. It's you know, in a continuous process of transformation. So we decided to set a few rules and then to provide an algorithm. The rules were we would have a wall of a certain height that we defined. It would be 100 meters long, so you could move stuff around but not make it shorter and not make it longer. So the amount of material was precisely limited. And this wall would have a behavior, and the behavior would be dictated by structure. You know, just the fact that you need to produce this wall in segments of about 3 meters, and if you don't curve the first layer, then it would just tip over. And if you know this pavilion, or most of the pavilion, could not drill holes and put foundations, so things have to stand. And with a certain curvature, this works. Here the black line is the first layer. So you see this thing, you move it around and it searches automatically for solutions that allow the thing to be produced. So it's I don't know the German term, it's Verfahrensgerechtigkeit, you know, if when not just the material, but when it's the process itself, you know, that tells you how things should look at the end. And like in the other project, once you have this information, you can just ask the system to give you each single position for each single brick to make the elementation. I think that would be crazy complex. That would ask, you know, need weeks of manual work. Here can be done literally in the last minute. Once the production time is, or once you need to start producing, then the curator needs to give you the last line, and then you produce all this information, and then you are able to assemble this extremely complex, very, very thin wall directly. Good. Another example, this is our institute building in Zurich. Here we were super lucky. This is a once in a lifetime that when the president of the school asked the faculties to design their own building. I never heard about this. Probably they wouldn't do it the second time. And inside this experiment, we designed and produced this roof here as an experiment. The system, the constructive system, is similar to the brick experiments, similar in the sense that it's just a stacking. It's 2.5 dimensional. Different because it works with slats or timber, linear timber parts that can be processed in line. So you don't have to pre-cut them all and then to find the right one to place it in the right place, but I think we'll see in a minute you do this in the process. So you have this degree of freedom to cut to a length and to cut to an angle and then to nail stuff together. And this image is nice, or plan, you could call it plan, because it's the only one existing. Everything else is data. It's not meant for assembly or for production, but it's meant to show a characteristic of a constructive system at this scale or of this resolution, which is that it becomes almost textile. You can stretch. You can stretch. You see at a certain points. Is this a pointer? Yeah. No. Yeah. Like here, for example, you have this opening, this duct, smoke duct. Normally, you would cut just through your structure and then fix it somehow structurally, and then have a hanging ceiling that hides everything. And here you just ask the structure to create space for this vertical element going through. The system behind is nothing new. It's just a truss, an upper chord, a lower chord, and diagonals. What is different is that these parts don't need to follow any rule, any repetitive rule, because as long as certain constraints are met, this can take any form. Yeah. And the addition of such trusses creates the roof. In order to be able to do this, here I show it in a bit more explicit way. You need to design your constructive system and your design system. So these both ends are important, and they have to meet very carefully because they depend each other. And you have to, this is just a montage of here is on the right bottom, you have the design information, and towards the end you have the structural information. At the end it's BIM, BIM meaning everything. But the interesting thing is here, what are the interfaces we architects, that are also the designer of the system, want to be able to manipulate until the very end. So what are the fundamental, and this is, it doesn't matter how we design, we always need to understand what are the handles, the thing we want to be able to control, because everything else then has to be automatic. This is 50,000 parts, timber parts, all different. Almost 1 million nails, all different. And all of the nails, they're all similar, identical, but the pattern is different, because you see here it's a pretty dense thing, and you have certain rules that are dictated by timber code that you cannot negotiate and you shouldn't negotiate. And you have to find there in this feasibility area where two parts overlap the best, or let's say maybe they are often the only option to fit the nails you need, because you have this information from structural analysis, and then you start to discover in your constructive or design system certain degrees of freedom that are extremely interesting. So you depart from a problem. The problem being that this is 6 nails and there is no way to put the nails into these overlapping areas. But then you understand there are two ways to react. One is to extend one slat. You know, this is cheap because it comes for free. It's slightly more timber, but doesn't matter. You know, all the rest stays identical. And this extends your area. And if this is not enough, the second thing you can do is to increase the size of the slat. And of course, this is not, you know, this has to happen in step because you cannot have a big number of different slats. So this becomes part of a system that then, of course, allows you to do some optimization. And optimization, you know, it's a good thing. You see there, we can save a lot of just not going for the worst case, what normally we do, because we have no idea about what's happening in our complex structures. Here we don't just take the worst case as a ground truth, but we say, you know, we choose for three different. Now I have skipped this slide. We just choose for three different because we agree with the contractor that this is reasonable to have three different slats in the process, and then we just allocate the right one at the right place. And we'll see here. Yeah. Again, the process. That is like the brick one, very, very basic, simple. Just these two cuts here are added. What is not so different, I put in the glue. It's just understanding how to rotate the blade. And then the printing process that now just is bigger than last time, but it's analogous. So it's layer by layer, and then you put the nails. And once the parts are prefabricated or assembled, you bring them onto, or let's say you install all the subsystems. This is sprinklers and lights and stuff, and then you bring them to the building site. Yeah. Maybe I move on. Yeah. This is a diagram showing what implication this way to think about constructive systems and or design system has. You need to be able to automate almost everything. Because if you deal with large amount of data that we are not able or not good at manipulating, then we need to be able to transmit. Let's say the design data has to go directly to the structural engineer without him needing to remodel anything, because to remodel something, if you have 50,000 parts, is a lot of time. It's prohibitive. The same check after he has analyzed what forces you have in the joints, you automatically need to be able to check what does this mean for connections. So this the story of the number of nails, and this have to give feedback to the designer. And this iteration is not a 3-time iteration. This is normally what we do in a traditional design. So we do something that we change second time, and the third time we're already arguing with everybody, because everybody wants more money, you know, and asks us to be more precise, you know, and to do it right the first time. Designing is iterating. You know? And this system gives us the ability to really iterate through things. And here you see the roof. You see also this seams, you know, where things are nailed together. They look as they would be not precise, but they are super precise. They are just the consequence of this optimization step. You know, some of them got a bit longer. You know, and I think this slight blurring where this machining precision gets scrambled through a bit from other logics is extremely interesting. You see it here. But at the end of the day, what I wanted to underline here is that we start from a system which has 50,000 parts, all different, that we impossibly could handle. And by defining a clear constructive system and design system, we can break it down machinically both in design and in this prefabrication process, to just 168 trusses. And 168 trusses is nothing. I can print it or sketch it on an A4, bring it to the building site, and nobody will have a problem with it. Next project. Yeah. Now I want to switch material system, but still talk about constructive system. So it's not so much the material. Here the material is also interesting or not interesting, depending. This is polyurethane foam. This is a material that foams up, so expands its volume at the moment when you mix the two components. And we use this material this is a long time ago. It was a very important experiment for us, even though we didn't do anything with this material anymore. It was too complex, too difficult to work with. It was more of a conceptual eye-opener for us. Here we do nothing else than to print a path on a 1 by 1 meter panel with this material and try to understand what happens. Yeah. While doing this, the material foams up. So you see here you have two processes intertwined. One is the deposition process. This runs in time, and then you have the second one that starts exactly in the moment when the material leaves the nozzle. That is also a temporal process in time, which is the foaming up. Here you see the process, and here is the result. And this is extremely interesting because first question is this beautiful? I remember discussing this with students, and they being very sort of confused because they spent a long time working on these nice patterns, and then they get this, and they need a second to adapt and to understand that actually it's if not beautiful, it's remarkable what happens here. First thing is you couldn't produce this in any other way. There is no other way to produce this that fast. And if speed, this is where we started, and energy and this thing are taken into the equation, beauty also somehow has to relate, or elegance has to relate with simplicity in production. And the second thing it tells us is we should, in general, start to reconsider this very geometric-centric way to understand design or our physical environment, where we say, okay, this is geometry, and geometry then directly is the architecture, is the city, is the material, because there are so many other processes here, like the behavior of the material, like the timing, that have much more influence on the result. And this, is so simple that if you wouldn't, you wouldn't expect this to come out of it. And if you wouldn't have seen the video before, understanding the process that allows for it, you wouldn't understand. Here are other stunning examples. This is just two grids. One, just shifted by half of grid. So you have the material of the second pass-through that flows down on the two sides of the already foamed up part. So this leaves this very thin trace, and most of the material flows down into the hole and foams up there. And these are very controlled one. This one is very much out of control, but also interesting because theoretically this stuff is technically reproducible, only theoretically, because our environment is way too complex for this to happen. So it's a small variation in temperature in the air current and the machine and things, and you will get something different, but not so different. So there is a certain. Okay, we moved on very quickly to other systems that are much friendlier. This is sand. They're simpler, but also very intriguing. Preotto has experimented a lot of with sand. This has a certain tradition. And it has, as the foam, behavior or self-aggregation behavior that contributes to a very large extent to what you have at the end. You know? Same thing here, it's not a continuous deposition, but it's moving certain position and opening a valve and depositing material. And we have spent a lot of time experimenting, this mainly with students, what the relationship between time, material, and geometry being the position in space is. And this very ephemeral, beautiful thing. Then we did an experiment at some point where we wanted to use this. You know, this is still takes too long. You see how this is a thing you would never design. You know, this is also a matter of economy. You know, so how can you instrumentalize things to do something for you that you would never be able to design or would never have the time to design? What boils down to the same. Even if you would be able and don't have the time because nobody pays you, you know, then you should find something that is smarter. So where the system helps you. Yeah. And then we use this to produce molds for casting concrete panels for facades. This probably wouldn't do anymore. This was 15 years ago. So why would you use concrete panels for facade? But back then it was a nice thing because a lot of these things were being done, crazy shapes, crazy designs, not really clear why, and then foamed out of styrofoam, producing a lot of waste. And this was the counter proposal. This is a system that is circular because you see the sand gets re-inputted into the system directly. This ephemeral property is then catched by the concrete. And you have a very, very, very thin latex skin separating these things. These were then the results. Good. Now, do I still have time? Okay, 2 minutes. Then I rushed through this one because this is nice. You have seen we are moving from very, very architectural constructive systems like brick. I think there is nothing more architectural to experimental, a bit, playful things. And this is probably the most playful. Here we're questioning the 3D printer, you know, saying a 3D printer always needs this machine that is bigger than the building itself to deposit the material. And here we go for a machine that shoots the material, you know, literally through space, and allows us to decouple the size of the machine to the size of the building. Of course, it's very theoretical, but then we went. This is the strategy we often apply. We just try to see how far we get with such a thinking. You have the physics of the phenomena. They allow you to make pretty good prediction, but not to tell where things will land. In order to understand, in order to control the system, you need a feedback. And the feedback here in this small setup is given by a scanner. You know where the part will land, but there is the margin of error that depends, again, like in the foam, by many, many environmental factors. And this scanner tells the design system how to correct itself in order to be more successful. And then we perform this with clay. You see here material. We extruded the clay into cylinders. And we built a mechanism, a pneumatic mechanism that was able to just throw, you know, like an arm. The robot was too weak, the small robot, to do the action. So we had to decouple. What the robot does here is to orient this mechanism. You see it in this video. The charging, again, it's human. No? Let's see. No. And this is the architecture. You know, now this small experiment, it was part of a performance, was about demonstrating that such a very simple feedback system and a design system is actually able to produce something that is architectural, so something that has a vertical definition. You look at it. At the same time, if you look at these images here, has the process of its building inscribed. This is the all the scan data that was produced after each cycle, everything was scanned. There you see the thing. And this is extremely beautiful because here this constructive system becomes expressive. So these formations that still tell you once the mechanism has been removed and nobody talks about how it was done anymore, the deformation of the cylinder speaks about the direction it came from, the speed, the velocity, the impact, the already present obstacles on the place. Yeah. Okay. I think I will wrap up. Here you see one of the cylinders. That gives you the impression of how desperate trying to control something like this is. Maybe an engineer would do because it's ambitious. Maybe with some machine learning and thing, but eventually it's not needed. Eventually you just look at the result and you say, okay, it's interesting. Good. I have now, just to wrap up, show you constructive systems and design system. And my point is that as architects, we should first understand that this agency on data and the possibility to really design and shape with these complex systems is important, because it allows us to create efficient structures and also efficient in terms of beautiful structures in a very efficient way. And if we go back to the discussion on sustainability and all those things, what we need to achieve in architecture is to be able to do more with less material. Also with other kinds of material, but fundamentally we need to be able to do more with less material, with less energy. So we have to go for processes that automatically balance themselves or allow us to control them in a very efficient way with digital tools. Because it's only complex structure that really can make the maximum use of the material properties, being is concrete or timber or clay and so on and so forth. Thanks a lot.